Hello everybody. So today we're going to focus on probably the three major macronutrients in the soil. We're going to focus on nitrogen, phosphorus, and potassium, or NPK. The same three things we'll see in the majority of fertilizers that'll be used. So just kind of a quick little thing. I like this picture that we used, nitrogen. We can see that in our green growth. Phosphorus, we can see that in our flower, fruit, and root growth, and potassium in our overall health. So we can kind of start to diagnose what the problems may be just simply based on looking at certain parts of the plant. So in terms of plant nutrition, or the nutrients in a plant, it's divided into three categories. So you have your major elements. So you have carbon, hydrogen, and oxygen. Those come from the air and the water, and they make up the carbohydrates in the plant. And then you have your macronutrients, and that's where we're going to focus our attention today. So macronutrients, the three big ones: nitrogen, phosphorus, potassium. Then you also have calcium, magnesium, and sulfur. And these come from special bacteria. They come from decaying organic matter. They can come from material or minerals weathering in the soil. And then you also have micronutrients. So you have iron, zinc, manganese, cobalt, copper, molybdenum, sodium, chlorine, sometimes silicon, and some other ones. But our NPK, our nitrogen, phosphorus, and our potassium are the three most important macronutrients. And so here's just a kind of a quick example. If we were looking at our plant and we said, well, the foliage doesn't look great, or the color doesn't look quite right, we might be thinking we need some more nitrogen. If we were having some problems with the fruits or the flowers, well, we might be looking at phosphorus, or even possibly then when we're looking at the roots too, could be a phosphorus issue. Or potassium could be roots, and really making sure that we want strong roots. And so if you look at the right here, this is kind of a little cartoon drawing of a bag of fertilizer, but you'll see three numbers usually on a bag of fertilizer, and those three numbers, they're NPK, so it's always in the same order: nitrogen, phosphorus, potassium. And that's how you'll read what's in the bag. And so there's a couple different ways the plants are going to get nutrients. One of the ways is mass flow, so carried in gravitational water. So that is on our bottom left there. The idea that as the water works its way down through the soil through the force of gravity, that the nutrients can be moved from place to place that way. Another one is the idea of diffusion. So from areas of high to low concentration in soil water. And so we see that in the top picture there, where if there's an area of high concentration, then it'll move to low concentration, and then that movement can free up some nutrients as well. And then there's also the idea of interception there on the bottom right, where roots grow into the areas of nutrient concentration. So we can see our roots trying to extend in to that soil water. And so that's just some of the different ways that nutrients can move throughout the soil and end up in different areas. So how do the plants get them from the soil? So that's where the plant roots come into place. So the root cells contain membranes that are semi-permeable, so certain ions can come in, but some other ones can come out. And we've got two forms here. So we've got passive intake, we've got active intake. So in passive intake, water and nitrate flow easily into root cells under normal conditions. When you've got active intake, phosphorus and potassium are taken into the root only by opening and closing special doors in the membrane, which takes energy from the plants. So the first step in the exchange of cations with hydrogen ions on the outside of the doors on the root membrane, and then the plant uses energy to open the doors and move the cations into the interior. So you've got to have a first exchange to even get the door open, and then the plant's going to use that energy to kind of open this door in the membrane to let the cations in. So we've got passive intake, which is our water and nitrate flow under normal conditions, and then active intake, where the plant has to undergo this certain opening and closing in the membrane that allows it to take up that extra energy. So right here, just looking at kind of the idea of what we're talking about here. So we've got in an acidic soil and why pH kind of becomes important. In an acidic soil, we can see that phosphorus gets taken up somewhat easily, but then there's other things like the iron, the aluminum, and some other phosphorus that are locked up. In the alkaline soil, we can see there's some phosphorus that can get taken up, but the calcium and some of the phosphorus is locked up as well. But when the soil is just right in terms of pH, we can see that we get more phosphorus taken up, and there's still all the calcium, iron, aluminum, and phosphorus all still sitting there available, ready to be taken up. And on the right, the idea of effectiveness at the root level, we see the idea of we got the first step. The hydrogen ions are going to bind in. They're going to open up the doors on the root hairs and the root membrane, and that's going to then allow for that phosphorus and potassium to then be able to latch on. So that's what we were talking about before with the active uptake. So with our active uptake, we've got this first step of the hydrogen ions bind on, open the door, and then the potassium and the phosphorus can come in. So let's talk about all three of these things. So the first one, and it's the most important agricultural nutrient, is nitrogen, the N. So we can see in the pictures down here at the left, we got a leaf that has yellowed versus a nice healthy leaf, and so that's one of our big kind of clues that say, oh, this plant might need some more nitrogen. Most of the nitrogen's locked up in organic matter or in the soil as that inorganic N2 gas. So we need things in the soil that are going to be able to do that nitrification so that we can get that N2 gas to be converted to a form where we can use it. So if we have forgotten what that is, that's called fixation. So when nitrogen is converted from an unusable form to a usable form, that's called nitrogen fixation. And on the right here, that's a picture of urea, where that's a fertilizer that holds a good amount of nitrogen in it. So how does fixation happen? If we get it all the way down to the microbial level, there's a special enzyme called nitrogenase. And it's a symbiotic relationship. So it's the bacteria inhabiting on the plant roots, and that's kind of what we're looking at here in the background picture. And you got mostly rhizobium bacteria in the pea family, and that's also known as the legume family or the bean family. And that bacteria then is going to do our nitrogen fixation and going to change it from the N2 gas form to ammonia. The plant, in exchange, because it's a symbiotic relationship, is going to provide sugar and a place for that bacteria to live. And the bacteria can fix up to 330 pounds per acre of nitrogen per year for a host plant. So that's the symbiotic version. The free living version is you've got bacteria just living in the soil rhizosphere. And so those bacteria can fix about 50 pounds per acre of nitrogen per year. And so here's kind of the idea of how that works. So we've got our legume, peas, beans, anything in those families. And so we have our nitrogen gas in the atmosphere. It then turns into, or we get our special enzyme called nitrogenase. And that's going to take our nitrogen gas and turn it into ammonia. And that ammonia then can help with the amino acids and the ureases. And all of that is the nitrogen fixation that's happening by this bacteria in the legume. That's the work that it's doing, is taking that nitrogen gas, turning it into ammonia, and then that way it can work its way into the soil and into the plants and be that useful form of nitrogen. So the mineralization of nitrogen. So soil organic matter usually contains only about 5% nitrogen, and it's only usable when it's released as NH2, which, as we know, is kind of a halfway in between. And so natural decomposition releases about 80 pounds per acre a year in rich soils, much less in our western soils out here where we don't have as much organic matter. So we have nitrification. So that's when ammonia becomes nitrate. And so plant roots cannot take up ammonia directly. It's got to be changed into this other form, this NO3 nitrate form. And so you have several soil microbes. The two examples that we give here are Nitrosomonas and Nitrobacter. And they can do this within weeks in warm, wet soils. Takes longer if it's not a warm, wet soil. So here's kind of an example of that. And so we've got our atmospheric nitrogen, our N2. So sometimes it can be, we can see it in fertilizers too, but it works its way into the soil. Once it's in the soil, we have our plants, our legumes that can do the fixation, get it turned into ammonia. And then we have our nitrification process, because we got to take that ammonia, make it into a usable form, which is nitrate, and then it's available for the plant to take. Sometimes that nitrate is going to leach, so we'll have our nitrogen losses, so we get some nitrate just leaching into the other parts of the soil. A bad thing that happens with that is the idea that it can pollute groundwater. There's about 20 pounds per acre of loss per year, and you can use ammonia fertilizers to slow this leaching down. The other thing that's going to happen, the other way we're going to lose it, is denitrification. So denitrification is just the idea that the nitrate doesn't get used, and then it turns back into the gaseous form of nitrogen and goes back into the atmosphere, and that accounts for about 15% of loss of available nitrogen per year, and that's done through some certain soil bacteria. And then the other way you have it is through volatilization. So the ammonia can just vaporize off and become atmospheric nitrogen again. This happens in our basic soils here, and it can account for about 20% of the nitrogen loss. So fertilizers. We talked about urea briefly before, but we also have anhydrous ammonia. So that's an NH3. So it's a fertilizer that's relatively cheap. You apply it with injection machines under pressure, and it's hazardous, it's caustic, and you definitely have to use protective equipment. The other one that we already talked about, the urea. So the liver actually can form urea by combining two ammonia molecules with carbon dioxide molecules. So it's a natural part of urine, but then they decided to make this synthetically and turn it into a fertilizer. It's got a slow release. It's very safe. It's moderately priced, and it can come in a granular or liquid form. The granular form is what we saw in that picture previously. So on the top left here, we can see our anhydrous ammonia, and this is the idea of what's happening as to how it gets applied onto the crop, and then you can kind of see a picture of that down below on the left and how it's getting sprayed onto the crops. And then on the right here, I wanted to put this one in because it's I thought it's interesting, the idea that it kind of shows what happens to 100 pounds of nitrogen fertilizer. So if I put 100 pounds of fertilizer onto a crop, what's going to happen? And so what's going to happen in this specific instance is about half of it's going to get taken up by the corn plant. So about 50 pounds of it gets used by the corn plant. Microbes in the soil are going to tie up 25 pounds, and then you've got 25 pounds that's just going to leach down or is going to denitrify and turn back into atmospheric nitrogen. So when you think about it, you say 100 pounds, that's a lot. But then when you start thinking about, well, the effectiveness of it's only about 50% of it's going to the actual plant, then that starts to become a lot less. And you kind of start understanding why we have to apply so many pounds and pounds and pounds of fertilizer to get it to work for large areas. So a couple other nitrogen fertilizers, so ammonium nitrate. So this has a very rapid availability of nitrate and ammonium that can be held in the soil for later use. The one thing that sucks about ammonium nitrate, or hopefully you think it sucks, is that it can be used to make explosives, so it's not really sold much anymore. And then there's also ammonium sulfate, and it also supplies sulfur, which helps out a lot of plants. This comes in a granular form, especially if it's non-commercial use, and it's a strong acid former, so it can be great for our soils. And it really depends on, if you have an acidic soil, not going to be great, but if you have a basic soil, it can be very helpful. So others, you can have organic waste like compost, manures, and sludge, but they only have about like 1 to 8% nitrogen in them, and so they're going to be very expensive to apply to large areas because you're going to need tons and tons and tons of it. And so that just doesn't become economical as a fertilizer, just kind of an organic amendment instead. And then you've got these other slow release formulations, so some mixed formulations that release over extended periods. Some things you might hear or see: polyform UF, ureaform, osmocote, sulfocote, and they're all very expensive, and usually you'll see them used for like ornamental plants or things where people are willing to pay the extra money to use those slow release formulations. So one of the other things to discuss and really make sure we understand with our soils is that they can be, or our fertilizers in our soils, is that they can be problematic. So we talked about the idea of leaching and possibly getting into the groundwater. Another threat is that rain and irrigation can run off and end up in our waters, and that can lead to things like eutrophication, where you get algal blooms with the summer heat. The idea of manufacturing the nitrogen fertilizer is very energy intensive, and it uses natural gas, and so you're going to be creating lots of emissions. And then the idea that the microbes in the soil, when they convert nitrogen fertilizer into nitrous oxide, that's also going to be a greenhouse gas, so that's also going to damage the ozone layer. So we got lots of different things happening when we put fertilizers into the soil. So it's something we really got to consider, that if we're going to do it, it needs to be done right, it needs to be done correctly, it needs to be done where we use the least amount possible to try and prevent the problem. Our second of our big three macronutrients is phosphorus. So it's the second most important nutrient. That's why we talked about nitrogen first. Now we're talking about phosphorus second. It's needed for all energy reactions in plants and animals. It's the most important nutrient for legumes in the pea family. So that's actually really good to understand, because they're nitrogen fixing plants, but they need that phosphorus so that they can do the nitrogen fixing that's necessary. So it's a nice balance, and kind of puts together that idea of the ecosystem and how things work well together and are needed for each other in an ecosystem. You usually got plenty of phosphorus in western soils, but only very slowly released from the soils to the plants. So you kind of need fertilizers if you're going to do like farming on a commercial level because you kind of need it to happen quicker than it actually is available naturally. So, where do you get phosphorus? You can get it from minerals, apatite or rock phosphate. That's the most common soil mineral that contains phosphorus. It slowly hydrolyzes to phosphoric acid via several insoluble intermediates. And this happens fastest at a pH of 6.5. So, once again, why knowing pH can be helpful. And then mycorrhizal fungi will help break down the minerals much faster, and it moves in soil solution relatively rapidly once it's hydrolyzed. So one of the other big things with organic matter is that up to 80% of phosphorus comes from organic matter. So supplies that's about half the phosphorus needed in crops in the Midwest, but much less here. So it's the phosphorus gets broken off from the soil organic matter by a phosphatase enzyme from the plant roots and the soil microbes, and then phosphatase is also a major enzyme found in mycorrhizal fungi. So I know we've seen the nitrogen cycle, but let's take a look at the phosphorus cycle. So we can have animal manures and biosolids and plant residues, all those things that end up becoming our organic matter that can give us organic phosphorus. And through our mineralization, we can get our soil solution phosphorus. We'll get probably some leaching from that, and then that's when our plant is able to take it up. And then how do we lose phosphorus? We can get it to precipitate to secondary components, or it can be adsorbed by the mineral surfaces like the clays, the irons, aluminum oxides, or carbonates. And then you also have runoff and erosion, where we could lose it as well. So some phosphorus fertilizers. So you can get pure rock phosphate, which is that ground up apatite. It's about 32% phosphorus, but really, like, pretty much none of it is quickly available to the plant. It's a cheap fertilizer, but usually you have to do further refining to make it useful. And you got phosphoric acid is another one. It's a byproduct of the refining process, but it can be a fertilizer itself. It's about 40% phosphorus, and much of that is actually immediately available to the plant. You can usually get this in a liquid formulation, so you're going to need some special application equipment. And then there's superphosphate, which is hydrated calcium phosphate, which is a very common fertilizer. It's about 20% phosphorus, but it's pretty safe. So here's just some examples. Again, so a starter fertilizer, you're going to see kind of that higher amount of phosphorus. If we're trying to just maintain our lawn, you can see it's a decently low amount of phosphorus. If you have areas where your phosphorus levels are sufficient or high enough, you might find a fertilizer with no phosphorus in it. And then if you just want kind of like a general fertilizer, you'll see something like 10-10-10, 12-12-12, that sort of a thing, where you're going to just basically, it's a little bit of everything, and it's really a general purpose, kind of just give it some fertilizer and kind of see how things go. Another phosphorus fertilizer, the idea of a concentrated or triple superphosphate. So it's less hydrated and more concentrated calcium phosphate. This is also very common, especially for home use. It's about 45% phosphorus, very safe, pretty expensive. And there's a bag of it, and you can see it's a 0-45-0, so that'd be 0 nitrogen, 45% usable phosphorus, and 0 potassium. But you really want to make sure, as we kind of talked about before, the idea that you're using the right fertilizer in the right place. And so, like for instance, with Lake Tahoe, the soils around Lake Tahoe contain plenty of phosphorus naturally. So if they get too much phosphorus or they get some runoff from phosphorus, it's going to be damaging to the ecosystem. So in that area, they want you to use fertilizers that have zero phosphorus in it because they already have enough phosphorus. They can handle some more nitrogen, they can handle some potassium runoff, but they can't handle any extra phosphorus. So it's really important to think about what region you're in and your use of the fertilizer and which macronutrients are going to be helpful and which are going to be harmful. Our third of our three is potassium. So the total potassium in soil is huge, especially in the West, but it's usually tied up in soil minerals and not soluble. It's harder to kind of get it to move around. You can get it through very slow weathering from mica and feldspar. About 150 pounds per acre is available in most soils at any given time, but if you're going to do high production commercial farming, you're going to need more than that. Potassium is needed for the plant cell membrane function, and including water uptake and disease resistance. So potassium still has its role to play, even though it's not, it's tied up in soil minerals and you need it. It comes from very slow weathering. It's still the idea that it serves a function, and water uptake, disease resistance is usually pretty important when we're talking about plants. So potassium still plays a very important role. If you have acidic soils, it's very non-soluble, so you need more applications back east than you do out west. There we go. So if we look at our potassium cycle, because we looked at our nitrogen cycle, we looked at our phosphorus cycle, so let's look at our potassium cycle. So you can get it through a fertilizer. You can get it by through exchangeable potassium in the soil from organic matter, clay minerals, or sesquite oxides, or you can get some fixed potassium. So you're going to have zeolites or vermiculites or things like that to get it in there, or you can have that structural potassium where it's happened over that long weathering process where you can get it from the feldspars and the micas or other minerals that have potassium in it. How do we lose potassium in the soil? Well, once we got it to the soil solution, it's either uptaken by the plant, or it leaches out, or it can go back into those vermiculites, zeolites, the fixed potassium, or back to the exchangeable potassium, back into the clay minerals, organic matter, or sesquite oxides. So, specifically in terms of losses of potassium, you could have what's called luxury consumption. So many plants will just store potassium in higher amounts than needed for good growth, and they can store a lot per acre, and they're only released after the death of the plant. So basically, they're hoarders. They say, well, I might need this someday, so I'm just going to hold on to it. You can also lose it through the soil microbes, which can concentrate potassium up to thousands of pounds per acre, and then also released upon death, this time of the soil microbes. The clay particles we talked about, that's how you can get potassium from the clay particles, but you can also lose potassium to the clay particles, and they're held tightly in ion exchange, and sometimes they're just held on too tight that the plant roots can't get them, and so the plant roots kind of have to force them loose in some soils. And then just the idea of leaching, but that's really only happens in terms of potassium if it's a sandy soil. So potassium is also important in terms of water movement. We kind of talked about that a little bit, but potassium drives the water movement, helps distribute nutrients where they're needed and keeps the plant inflated and cool. And it regulates water loss through the opening and closing of the stomata. And so potassium is really important. And that's why, going back to the beginning of the lecture, we said when you're looking at the overall health of the plant, that might be a clue towards potassium, because really when you think about this, the idea of water movement and providing minerals to the plants and the kind of function of the plant being dependent on potassium, that's the idea of why it's the overall health of the plant that can be affected by potassium, as opposed to just, you know, the coloring or some other problem in terms of like the fruiting or the flowering. You have to kind of look at the overall health of the plant to really know if it's a potassium issue. So how do we get potassium? You can get through mineral weathering, and we said especially mica and feldspar, and that's going to be a main method in low organic matter western soils. Is just going to be this kind of longer term mineral weathering. Organic matter breakdown, because if it's in the organic matter, then you can get it out there. And in terms of eastern soils, where it's, you know, warmer and more moist, then that's going to be the main supply mechanism. There is the breakdown of organic matter, and then also the exchanges that we talked about. It can depend on the clay type, but that's still pretty slow in comparison. So what fertilizers do we have then? Because we talked about that with the other two. So we got potash. That's the #1 potassium fertilizer in the U.S. So that's potassium chloride, and that's mined in the western U.S. Utah and New Mexico especially is where potash is mined. You can also mine it from salt brine in salt lakes. The addition of chlorine, though, can be a problem, and you get about 50% usable potassium in this potash. Potassium sulfate is similar to potash, but you don't have the chlorine, but you get that good source of sulfur, which a lot of plants don't mind having. Potassium sulfate, though, is more expensive. And this is what it looks like when you're, this is a potash mine, and what it looks like when you're mining potassium out. And this is kind of the overview of what that looks like. So what's right there in the middle of the picture, that's a potash mine, and we got some evaporation ponds in the background behind that. This is a potash mine right along the Colorado River, that nice brown sediment filled river with a nice riparian buffer. That's the Colorado River. And if you're following along in the PDF slides, which I always encourage you to do, you can click on this NASA link and get a little more explanation about this picture and this specific potash mine. And so these last two slides are just kind of like the other lectures, leaving you with some questions to answer, just kind of getting you ready for the test. And hope you enjoyed the lecture about our NPK, or nitrogen, phosphorus, and potassium.